I want to now start talking about some of our papers. So the next task I have assigned to you is to go read some more papers. And now we're starting to go from, we've covered reinforcement learning and supervised learning and unsupervised learning now. And by the way, I have to admit, we have only touched upon all of these very, very briefly. In unsupervised learning, we did not cover clustering approaches, and there's a lot of them, and there's some really good ones. And I guess I can go back and cover some more if you guys are interested. In supervised learning, we did not cover a plethora of things. We haven't really even touched on how to use neural networks in supervised learning very much. We didn't cover decision trees or naive Bayes or rule-based learning or a lot of or ensemble techniques or a lot of other supervised methods. And in reinforcement learning, we did that one a little better, but there's still a lot more going on in reinforcement learning. But suffice it to say, you guys get the general picture of those three types of learning, right? Okay. Next, I want to start putting them together. Here's a paper. It says, what are the computations of the cerebellum, the basal ganglia, and the cerebral cortex? And you know that law that says whenever the title asks a question, the answer is always no? That doesn't work here.
No.
No. In this case, it's, I can't even remember the name of that law now. Things are just not coming to me today. I don't know. Doesn't matter. The answer is simple. This paper claims the cerebellum does supervised learning. It claims the basal ganglia does reinforcement learning. It claims the cerebral cortex does unsupervised learning. And the main reason I'm assigning you to read this paper is to convince you that there is a way to put these things together, and the brain seems to do it, and there's a lot of compelling evidence to suggest, therefore, that we can build a full artificially intelligent cognitive architecture by combining the major products of science in the domain of machine learning. And I think that's an important thing too. So the cerebellum, in fact, there's a very vague figure right here. This is the back of your brain, and this is your eyeball goes right where my hand is right here. So the right side is the front. The cerebellum is this lobe in the back, lower side of your brain. For years it was thought that the cerebellum was totally in charge of motor control. That hypothesis has since been diminishing, and now it's believed motor control is more in the upper center part of your cerebral cortex. But the whole theory of this paper, and this paper is now 2 decades old, so this is not bleeding edge neuroscience. This was big a couple of decades ago, and this will spin off into lots of other things, other research that's since been done. But they're going to claim that the big main part of your brain, the vast majority of the area, is dedicated to unsupervised learning. And that's interesting to me, since a lot of machine learning can't figure out what to do with unsupervised learning. And they seem to focus mostly on this supervised learning part, which seems to be kind of pushed off to the back. Less important parts of your brain. That's pretty vague. There actually are more neurons in the cerebellum than other parts of your brain, so you could argue that's very important. The basal ganglia really strongly seems to do supervised or reinforcement learning. This is the part that you have problems with when you get addicted to drugs and when you have anger management issues and things like that, because basically you generate dopamine in inappropriate quantities and it just causes behaviors that aren't good. Yeah. Well, let's see. I mean, it's not clear to me that reinforcement learning and memory necessarily go together. So, in fact, memory is kind of an interesting concept. One could argue that weights are memory, because the weights between neurons that decide when they activate encodes concepts that you have encountered before. And more specifically, if there are mirror neurons, when those mirror neurons activate, they would only activate for particular concepts if you recognize that concept, right? You see how that's a type of memory? Well, what causes them to activate is the weights. And so anything that tunes weights, in a sense, is a form of memory, And you'll find that exists all throughout the brain. So memory isn't really a specific part of the brain that has a database like we do with computers. You don't usually have a memory chip. It's more like memory's everywhere. Memory's kind of all types of learning have to have some kind of memory. There's memory in reinforcement learning, there's memory in supervised learning and in unsupervised learning. Now, I probably won't have time to go through this very well, but I just want to show you some of the equations here and make sure you can relate to them so that when you read the paper, this paper will make sense to you. Let's look at the supervised learning section here. Y equals f of x. Everybody get it? Pretty simple equation. The idea is inputs go in, outputs come out. This is the general structure for supervised learning. Okay. Here's another equation. What does this one mean to you? Yeah, this is the idea of an error function. We're going to say for the inputs that we expect, this is the expected E, not the summation sigma or some other E. It's given the distribution of inputs that we are likely to see, the corresponding prediction that we make is y hat minus the prediction we wanted to make. And we're going to square that all, take the magnitude and square it, to suggest that this represents how bad our supervised learner is doing. And if we find the weights that minimize this equation, then we have done effective supervised learning. That's the same as suggesting that if you compute the prediction based, wait a minute, they made a mistake. Hat implies that it's the predicted value, but over here they're computing a predicted value. This one shouldn't have a hat over it. Haha, I just found a bug in the paper, I think. Yeah, they might actually mean the hat is the expected value and the not hat is the predicted one, but that's not consistent with usual notation. Okay, and here they're showing how you compute the value, the activations of individual neurons in a linear model. Okay. I don't have time to go through these other equations yet, but here's what I want to show you is later on in the supervised section, they talk about the anatomy of the cerebellum. And they talk about this neuron, these neurons are connected to those neurons, and there's a figure here that describes how they see things as being connected with various types of neurons. Then they talk about the physiology, which basically says this activates that and this activates that. It's important to note that these circle dots and filled in dots have meaning. Dark dots mean that there's a excitatory connection. That would be a positive weight. It means if this one activates, it causes the other one to activate. The open dots indicate an inhibitory connection, which means if this one activates, that means the receiving neuron is less likely to activate. And so by identifying that, they can show that the connection of the brain forms this circuitry, which then they argue in the theoretical models. See here they refer to 4 and 5. When you see numbers like that, that's not a citation, that's referring to the equation that we just looked at. And those equations are the equations for supervised learning. And they're basically showing that, hey, this part of the brain implements circuitry that looks like the equations for supervised learning. And the paper is going to do the same thing with unsupervised learning and that other type of learning that we learned. And thank you, reinforcement learning. And that's going to basically show that, hey, look, it looks like we can start to tease out what some of the parts of the brain are actually doing. And then they show how that leads to how to start putting them together.